Okay, so now we're going to be in chapter 6, which deals with equilibrium. There's a lot you learn about equilibrium in general chemistry, and we need to remember that stuff. But from here on in, what we're going to be doing is we're going to be approaching it from the standpoint of chemical potential, which we didn't introduce in general chemistry at all. But now we're equipped with more sort of mathematical skills, more of an understanding of how thermodynamics works, where we can approach it on a deeper level. We're going to analyze this like your book does. We have this reaction here that has reactants A and B. We're going to start with everything in the gas form, and what we'll see is though we kind of develop general expressions where we can just amend states and how we deal with chemical potentials of different states. So everything that we do for gases, it'll actually be applicable for most species with minor changes. So we have these gases that are reactants A and B. C and D are products. VA, VB, VC, and VD, those are the stoichiometric coefficients. All right. We're going to say that we're going to have the motion be to the product side. So remember what this double arrow means? You could go left or right. And remember, like, when we write a reaction, it's like us writing it on paper. The reaction doesn't know how we wrote it on paper. The chemical potential is going to predict whether it goes to the right side or the left side. So let's say that we understand that it's moving towards the CD side, so we ourselves just write it on the product side. And so we're not really losing anything in terms of a general approach because we know the reaction is going to progress to the side that the chemical potential dictates. So we're going to say, say we know for this reaction, it goes to the product side to start. How much each pressure changes. So we're going to monitor the pressure of each one of these species. The amount of change in pressure depends on the stoichiometric coefficient. So remember these arguments that we made before when we were talking about kinetics? Those same ideas apply now. It's not a kinetics argument that I'm making, but it's the same ideas. For example, if we had a simpler reaction where we had 2A going to D, remember we made arguments that were like, okay, well, how fast does A disappear relative to D being made? Well, this stoichiometric coefficient of 2 tells us that 2A disappears to make a D. So it looks like A disappears twice as fast relative to D being made. In thermodynamics, we take that same idea and we define what's known as the extent of reaction. All right. And your book uses that funny symbol that looks like this, but I can't draw that over and over again. So I'm going to just use epsilon. Okay. So our extent of reaction is going to be epsilon. And what we'll do is we'll say, okay, well, with that same idea, if I have a species in my reaction and I'm looking at the number of moles it has, right, the change in the number of moles, right, could be plus or minus depending on the motion, all right? But if I define an extent of reaction, right, as this change in general moles, then the stoichiometric coefficient is what dictates how many of those specific moles change as a general change is enacted. Now, that's a mouthful, and it's a little bit difficult to understand until, like I said, you kind of apply an example to it. For instance, here's how the extent of reaction is defined in terms of this simple example. If you would look at DNA, all right, the number of moles of A that change are influenced by this too. It's influenced by the stoichiometric coefficient. So as A changes, right, if we define just a general change in the reaction, the change in moles of A happens twice as fast as the change in moles of D. Let's say we have a net motion to the D side. D will be produced, and we'll use a positive value there. If we have a net motion to the D side, the change in moles of A, right, would be negative. This right here, in the context of extent of reaction, is everything that we said when we just analyzed this from like our kinetic standpoint. Everything we say here should make sense. If I look at the change in moles of A, it happens twice as fast as the change in moles of D. So I just define this general change as the extent of reaction and I go from there. An important thing to note is to keep the units consistent on the left and right hand side of this equation, extent of reaction must have units of moles. All right. So why is this helpful? Well, it lets us just kind of define, all right, a general change, right, in the context of specific changes or vice versa. So now let's analyze this, right, from the standpoint of isobaric and isothermal situations, right? So let's look at constant T and constant P, and let's think about what the Gibbs energy is for this situation. Why is the Gibbs energy important under these conditions? This is what's going to dictate spontaneity, right? Our G, we know, is a function of natural variables T and P. And for this reaction, it would also be a function of the number of moles of A, the number of moles of B, the number of moles of C, and the number of moles of D. We know that when we have systems where the number of moles can change, those are variables in our G. We also know that when we go to write a DG term, we aren't going to have a DT term or a DP term because we know they're constant. So we could write those in and then take them to 0, but we're going to save some time here and just write DG. Now DG is affected by these guys because we know that, I'm just going to write it in summation notation, all right? We'll have partial G, partial N sub I, T, P, and all other N sub J's, all right? D, N sub I, right? We made these expressions before, okay? All these other changes, right? All these other partial changes of the moles in the reaction are going to influence our DG. This should be familiar. Another thing that should be familiar is we can replace this partial derivative with chemical potential. We looked at expressions like this before, okay? So this in an isobaric isothermal situation is going to dictate the change in Gibbs energy. The change in Gibbs energy then is also going to direct spontaneity because of these conditions mapping G onto, all right, the second law of thermodynamics. So this is what we have. Now, for this reaction here, let's just make sure we understand this notation. For this reaction that we have above, dG is going to be equal to mu of A, D, and A, plus mu of B, D, and B, plus mu of C, D, and C, plus mu of D, D, and D, all right? Now, if we had more or less reactants or products, it would change, but again, we're just going to do it in the context of this, all right? And then we're going to develop some general ideas that we'll be able to apply, all right, for other situations. But this is essentially, right, the total change in Gibbs energy. Now is where extent of reaction comes into play. Because if we look at this, what we have is a bunch of different changes. But we know that these changes in the number of moles, we know they relate to each other. Because we know that stoichiometry is what dictates how fast things appear or disappear. So in the context of extent of reaction, and remember we're saying we're generally going to the product side, right? We know that dNA is going to be minus VA d epsilon. And we know that dNB is going to be minus VB d epsilon, right? Because remember, we're going to that side, so we're going to lose these reactants. dNC is going to be VC d epsilon, and dND is going to be VD d epsilon. So now we can see like the utility of extent of reaction. Instead of having 4 distinct changes, we know the stoichiometry. So what we can do is we can define things in terms of one general change, the extent of reaction. So what we do is we substitute all of these into each one of the appropriate spots. Okay. So if we do that, what we're left with is a d epsilon in every term that we can go ahead and we can factor out. And so what we'll have is minus VA mu A minus VB mu B plus VC mu C plus VD mu D, all of that is multiplying a D epsilon. So we have one change now, right? So let's rearrange this just a little bit, right? Let's write this as a dg over d epsilon, right? And this dg over d epsilon, hold on a second, it's being done at a constant temperature and pressure. So when I divide through by this, let's mark down that it's at a constant T and P, and that changes this to a partial derivative, all right? So the right-hand side doesn't change except for the d epsilon is brought here, and then we note down what's being held constant, so it looks like a partial derivative now. I can rewrite it again, minus VA mu A minus VB mu B plus VC mu C plus VD mu D. Now, importantly now, all right, we can start to think about what this actually means. And on this side, it's kind of interesting. We get something that's sort of familiar. This should sound familiar, right? Stoichiometric coefficient of the product times the molar Gibbs energy of the product plus stoichiometric coefficient of a product times its molar Gibbs energy minus the same things but for reactants. It kind of sounds like those table problems we do where we look up these molar quantities for a reaction. We note the stoichiometric coefficients. We do a sum for the products. We do a sum for the reactants, and then we subtract the two. We even did that this semester. It sounds like those sorts of problems. All right, so that's what we did to calculate a thermodynamic property for the reaction. And if I look over here, I get the same sort of idea. This is how G changes as the extent of reaction change. As you force a change in the reaction, this is how Gibbs energy responds. With both those ideas, we can relabel this, right? And what we're going to say is we're going to call this delta G molar, to keep units correct. This is the molar Gibbs energy for a reaction. It's the molar Gibbs energy for a reaction. And I'm just going to rearrange this side here. Vc mu C plus Vd mu D minus Va mu A minus VB mu B. All right. This is the change in Gibbs energy for this reaction as written with these stoichiometric coefficients. All right. Incredibly powerful, incredibly sort of, I don't know, it's the foundation where we use to sort of develop what you'll see like the rest of equilibrium. It's the foundational principle. This guy must be the total change in Gibbs energy for a reaction. And like I said, over here, it's different symbols, but you've done calculations like this before, right? Using tables for delta H or delta G. And you'll notice in the table, those values are molar, right? So now, how is this the foundation for the rest of equilibrium? Well, the previous chapters and the previous discussions we've been having have all centered around how we develop mu's and how mu's and chemical potentials dictate flow, okay? So what we're going to do at this point is we're going to say, all right, with some approximations, let's go back and let's revisit these mu's we've been calculating. Now remember, for this first reaction, we said we had gases everywhere, okay? So what we're going to say is let's pretend that we have ideal gases involved in this reaction. We also spent some time talking about mu's for ideal situations and then how we change these mu's while keeping the same mathematical form for systems that differ from our standards or our ideal situations. So we know for ideal gases, we'll start there, and I'll keep reminding you that we actually know what happens for non-ideal situations. But for ideal gases, we know that mu, all right, is equal to mu naught plus RT, the natural log of P over P naught. Now we have 4 different mu's here. So let's say that this is going to be a mu sub I, right? And this will be a P sub I. And we know that P naught, our standard when we were dealing with ideal gases, was 1 bar. That's important to remember. But if I look down here, I can now make this substitution for mu in each and every one of these spots. Okay? Now, if you look what happens, this VC, for example, is going to multiply here and here when you substitute it in there. So for each one of these spots down here, what we're going to get is a mu naught term and an RT natural log of P over P naught term, right? So let's make that substitution there into each one of these spots. Oh, and before I go on, remember what we said here, right? What do we like about this? We like its mathematical form. So even when we deviate from our standards, even when we deviate from our ideal situations, remember all our work in the previous chapters maintained this form. So everything that we write here is still going to be general because we established that idea earlier. We're always going to try to maintain this for our molar Gibbs energies, for our mu's. So let's make these substitutions. What we're going to get for delta G molar for our reaction is we're going to get and I'm going to gather things up. Remember how there's a mu naught term that comes from each one of these? I'm going to get a VC mu naught for C, and put a comma there, right? Plus VD mu naught for D plus, minus VA mu naught for A minus VD mu naught for D, right? Oh, sorry. This is a B at the end. Let me say it one more time for you guys. VC mu naught for C plus VD mu naught for D minus VA mu naught for A, right? Minus VB mu naught for B. You could keep these knots as superscripts too, all right? It doesn't really matter. Each one of these terms comes from that first mu naught term, but then each one of these, remember, also had a natural log associated with it. So we're going to get VC, all right, RT, the natural log of PC over P naught plus VD, RT, the natural log of PD over P naught plus, all right, minus VA, RT, the natural log of PA over P naught. I'm going to make this a subscript here, a superscript, minus VB, RT, the natural log of PB over P naught. So just to recap, we had this down here, which was our expression for the change in Gibbs energy for the reaction. We have a general expression for mu that we can substitute in. I gathered all the mu naught terms to start with, all right? And then I gathered all the natural log terms after that. So all we did here was we made a substitution in for our mu's. We keep track of what has a negative sign. We keep track of our subscripts to make sure we're talking about the actual correct species in the correct spot. So now this can be simplified. The reason I like to gather the terms in this way is if you look at this right here at the top and you compare it to this down here, right? Notice that this has the exact same form. It has the exact same form, except there are standard conditions associated with it. So this thing that I boxed in green, it looks like a delta G that we calculated, except under standard conditions. So everything here, because it has the exact same form, this must be our delta reaction G naught. That whole entire thing must be delta reaction G naught. Okay? Which kind of makes sense. If I made this a knot here, all these mu's would become knots. And, oh yeah, then I would be analyzing the reaction under standard conditions. And that actually just manifests from the mathematics naturally. For these natural log terms, we can also simplify. Each one has an RT associated with it that we'll be able to pull out, right? Each one has, all right, a stoichiometric coefficient out in front. But remember, and I'll just write it down to remind you, if I have a, the natural log of x, I can write this as the natural log of x to the a. Remember, the whole point of natural logs is they help us pull down, right, exponents, but we can go in the reverse direction, okay? We can take these and we can make them exponents, and then what I'll have is a sum and difference of natural logs. And I'll be able to simplify further. So let's make those two substitutions, and I will write down some intermediate steps here so you see what I'm saying. My delta G for my reaction, which may or may not be under standard conditions, right? We're keeping it general. Starts off with a delta reaction G naught, all right? Then we're going to have a plus RT, and then we're going to have four terms inside here. We're going to have the natural log of PA over P naught raised to the VA, right? All that's inside a natural log. We're going to have plus, man, I keep messing up subscripts. I'm glad I'm catching myself, but sorry for this. Let's do the products first. So we're going to have a natural log of PD over VD. Sorry, PD over P naught raised to the VD. Plus the natural log of PC over P naught raised to the VC. All right. Minus the natural log of PA over P naught raised to the VA. Minus the natural log of PB over P naught raised to the VB. So all we did was make our substitution for delta G naught, and now we pulled out an RT. It's multiplying all these four terms, okay? Kept track of what was positive. The products were positive, right? The reactants were negative. And then we used that natural log rule where we had stoichiometric coefficients out in front. And what did they become? They became exponential factors. They became exponents inside the natural log. What's the benefit of this? All right. We now have sums and differences of natural logs. And so we can write this as one term, right? So the next step is to combine up all these guys. Remember when I add natural logs, that's like one natural log where these are products. And when I subtract natural logs, it's like one natural log where these are divisors, all right? They go into the denominator, right? So I'm going to rewrite this as one natural log term multiplying our RT. And this is going to be the natural log of, give yourself some room, all right, PD over P naught raised to the VD, PC over P naught raised to the VC over, this is still all inside the natural log, PA over P naught raised to the VA, PB over P naught raised to the VB. All right. This is starting to look, hopefully, familiar relative to things you learn in general chemistry. There's like one kind of further simplification that we make. Ooh, yeah, this is P subscript D raised to the VD. there's one other simplification that we make in general. What we say is we remember what P naught is. We remember that P naught is 1 bar. So when I'm dealing with pressures inside here, if I just remember that they're in bar, then I can drop the P naught, right? And so we get delta reaction G is delta reaction G naught, remembering that the pressures are in bars, plus RT, the natural log, product pressure raised to its stoichiometric coefficient, times product pressure raised to its stoichiometric coefficient, divided by reactant pressure, hold on a second, raised to its stoichiometric coefficient, reactant pressure raised to its stoichiometric coefficient. Oh, this, right? What we call this in general chemistry is we called it Q, right? We called it the reaction quotient. And because we're dealing with pressures, we're going to label it QP, right? So all of this inside here, we would call QP. And whenever we dealt with equilibrium problems in general chemistry, it was always product stuff raised to their stoichiometric coefficient over reactant stuff raised to their stoichiometric coefficient. It came from chemical potential. This this equation right here, once I take this and I replace it with Q, because this is the definition we have now. If I replace this with Q inside here, and this is for gases, but again, it's going to be like applicable in a general way, which we'll discuss in subsequent videos, right? This is an equation that you used in general chemistry. The delta G for the reaction looks like delta G under standard conditions plus RT, the natural log of Q. All right, RT, the natural log of Q. Remember, and I'll stress this again, but just to sort of finish out our thought process here, because it's a lengthy derivation, but it's an important derivation. Remember what happens to Q at equilibrium, right? Q is, right, pressure of product raised to the stoichiometric coefficient, pressure of reactant, product raised to its stoichiometric coefficient over pressure of reactant raised to its stoichiometric coefficient. Pressure of all reactants raised to their stoichiometric coefficients at equilibrium, right? If these pressures are now equilibrium pressures and there's no more net motion in that system and the chemical potentials now have settled down to being equal for the reactants and product side, remember that at equilibrium Q gets relabeled as K, right? So essentially what we have here is a fundamental way of getting at spontaneity. And inside there we see there's reaction quotient information like we saw in general chemistry. And we remember that at equilibrium, this expression, because it's so special, gets relabeled as your equilibrium constant, right? So for this video, it's all about this derivation and being able to reproduce it and understanding the steps, okay? Make sure you kind of have the labels down. There are a couple instances where I kind of fudged things and went back and fixed. Make sure you kind of make those corrections. And as always, if something's just unclear, we can Zoom. You can let me know that you need help via email, whatever you need. But this is pretty incredible. All our chemical potential stuff led to this like fundamental equation that we'll be able to use for any reaction. We'll talk about why it applies for any reaction in a bit. But we'll be able to apply it for any reaction to predict what its delta G is. And as long as we're under isothermal and isobaric conditions, that will be able to predict spontaneity of that reaction.